Out amongst the cow pastures and logging farms, located just a few miles north of Livingston, lies a super high-tech science facility called LIGO, which stands for Laser Interferometer Gravitational Wave Observatory. Wow, that's a mouthful, I know. But exactly what does it mean? We'll find out soon enough. Hi, I'm Rob Moreau, your host of North Shore Gems. And join us today where we explore this truly scientific gem located here in the heart of Livingston Parish. And we'll find out just what goes on here. So let's get started. Ever since the time of Galileo, man has turned his attention to the sky, looking for answers to some of nature's greatest mysteries. But there are limits to what we can see. Professor Rainer Weiss of MIT is convinced that there is another way to study the universe, something that goes way beyond traditional telescopes. So instead of using a telescope, which detects light waves, he'll use an interferometer to detect gravitational waves, which are the result of cataclysmic events in deep space, and which literally alter the fabric of time and space. But before LIGO could be built, Professor Weiss had to overcome a skeptical scientific community.
People didn't believe in gravitational waves, and for complicated reasons, because it was one part of the Einstein theory that didn't quite fit the mathematics as well as other parts did. I won't go into that, but to fancy people, it wasn't quite a tensor they could find. They couldn't find a nice formalism for it. So consequently, there was a lot of skepticism, whether it was even part of the theory. Well, that got sort of ameliorated by when people discovered a binary neutron star system. Hulse-Taylor, the people who won the Nobel Prize for this, and in fact, the discovery of gravitational radiation has happened. It's indirect. It was an indirect evidence for it. I think, to me, it counted like a real measurement, you know. But we're going to directly measure it, and we're going to see something which nobody's ever seen before. What really goes on? Now, what's the joy of it is, and this is why I think it adds to astronomy in a way that is completely new. We're going to be seeing the actual motions of what goes on inside the objects that are doing the radiating. In other words, when you look with a radio telescope or with an optical telescope, what you see is the outsides of things, okay? And you might see a black hole, but you'll see it ejecting a jet. But when you don't see what happens when, let's say, two black holes get together, and let's say one is spinning and the other one's spinning, how do they actually perform? What do they do? Do they fly apart sometimes? Do they oscillate around each other? What do they do? And the theory has different answers for that. So consequently, we're going to be able to get something which is unheard of in astronomy. We're going to get the actual equations of motion of the objects that we're seeing by looking at these waves. That you don't get by any other technique that I know of. That's going to be the revolution. It's going to be a revolution where you're looking inside of something, which you couldn't do otherwise. And I think astronomers finally have come around to that. You know, in the beginning they were very skeptical, but now they're dying to, hey, when are you guys going to get ready? You know, they're taking bets when we will finally see something, you know. They want to get in on the action.
It all begins with Albert Einstein's General Theory of Relativity, which was published back in 1916. It describes gravity as a geometric property of space and time, or space-time.
And one of the predictions that made is that nothing can go faster than the velocity of light. There has to be a way that information in gravity gets around in a finite time, not infinitesimal time. In other words, you cannot learn something new quicker than what it would take the velocity of light to transmit the information to you. And so the thing is that he invented, in order to do that, something called gravitational waves. Much like Maxwell in the century before explained electromagnetic waves, which is the things that we see by and we have radio stations using, that they travel with the velocity of light. He invented that there was something that would travel with the velocity of light that is gravity. And that's what we're looking for. We would like to know what happens when gravity gets so strong that it curls up the space and nothing gets away from it. That's what a black hole is. No, it's so massive that nothing leaves it. No light, nothing can leave it. And so the process of doing that distorts the geometry so dramatically that it changes space in such a way that Newton could have never predicted anything like that. That is the real reason we're in this business. We would love to have evidence for what goes on around a black hole. And the way we would find that out is through the gravitational radiation that a black hole emits when it eats something. It eats another star. See? And that's, to us, the most exciting thing that we could possibly get out of this thing.
Okay, so how does this interferometer thing work? Simply put, an interferometer is a device used to detect very small changes in distance. It does this by splitting a beam of laser light and looking at the interference patterns created when they are brought back together. In the case of LIGO, those beams are shot down 2 4-kilometer tracks set at right angles.
Okay, so you have this thing that looks like an L.
Right.
And now what happens along that L is that when a gravitational wave, like say from one of these neutron star coalescences come along, or a black hole coalescence with another black hole, what it'll do is this. For part of that cycle, when it's going chirp, right, it'll take this length, which let's call that the north-south leg, and it'll shorten it a little bit. Make it a little shorter, but in the meantime, make that one a little longer. Right. And then it'll flip and make this one longer and that one shorter. So it's doing something crazy. It's doing something like this to the mirrors at the end. It's doing this. This goes out, this goes in. It's doing this. Right. That's the motion that we're looking for, like just that. And
that's your measurement.
And that's our measurement, and we measure it's the simplest measurement you can imagine. What we're measuring is measuring the time it takes light to leave that building way down there, to go down to this mirror way at the end over there, in the south. Right. At the same time, we're measuring the time it takes light to go from that building to the west, along the same length of path, equal times. It should take equal times, and when they come back together, we look at, did it really take equal times? And we set it up so that it's exactly equal times. We do that. Right. And then along comes this gravity wave, or gravitational wave, pardon me. Well, gravity wave is a different thing, much more ordinary. A gravitational wave. And we will look for the thing that disturbs the equality in that time. And that shows up in an interferometer, which is a device specifically sensitive to how long it took light to go this way and back behind me and to come together again. Very, very sensitive to that. And we have to measure something which is outrageous. And that's the thing that made it hard.
That something outrageous is the ability to detect movements as small as 1/1000th the diameter of a proton, all within a vacuum tube whose pressure measures an astounding 1/1 trillionth of an atmosphere.
So one of the sources that we're looking for are 2 neutron stars that happen to have found each other, and they're going around each other. We've seen things like that by radio astronomy and by optical astronomy, but now we hope to see what will happen as they get closer and closer, and they go faster and faster, and eventually they smash into each other. And that death knell of that binary coalescence, as it's called, the binary stars falling into each other, is something that we can detect in this device, and it'll sound like a chirp. It'll go whoop like that.
It's going to provide that change in the fabric.
In the fabric of space. It's a wave, and it has a very characteristic shape and a very characteristic spectrum. It's not something you're going to confuse easily with a train that's running down here in Livingston.
Right now, LIGO is undergoing a multi-million-dollar upgrade designed to increase its sensitivity by over 10-fold. Brian O'Reilly, the director of the upgrade project, who hails from Ireland, gave me a tour of the facility and the work they are doing on the upgrade. So I'm standing here with Brian O'Reilly, who is one of the staff scientists here at LIGO, and we're in the outside of the laser room, I guess, and there's a big danger sign here. So why can't we go in there, Brian?
So this is an antechamber to the laser table itself. We have very strict contamination control guidelines because with a high-powered laser, it's a 200-watt laser. If we get contamination on the optics on the table, it can burn in on the surface and damage those. So we try to keep contamination to a minimum. The other reason, of course, is a safety reason, which is why we have this danger sign. Our laser is an infrared laser. It's invisible to the human eye. You have no blink response to the laser light. So you could, in principle, get severe eye damage working with the laser. The laser was built in Germany by people at Laserzentrum in Hanover. It's a fundamental part of the advanced LIGO upgrade to go to higher power. The more power we can put into the interferometer, the more sensitive we will be to detecting gravitational waves. So this is one of the foundation blocks, if you like, of the advanced LIGO interferometer.
The advanced LIGO will be able to see a volume of space 1,000 times greater than the initial LIGO, and its range of observation will increase by a factor of 4 or more. So this is actually part of the upgrade of the new system here at LIGO that's actually going to provide a 10-fold increase in sensitivity of the laser. The really cool thing about LIGO is it's open to the public. In fact, LIGO's outreach efforts are unique.
Our job is to communicate the science of LIGO to the greater public. So we do field trips, we do teacher workshops where we actually train the teachers. We do particular just public outreach. Third Saturday of every month, we're actually open to the public from 1 p.m. to 5 p.m. And each Saturday we actually theme with a particular topic. So like this month, November, is popular science. Next month is light fantastic. So there's always some type of physics or science topic that will just kind of put new activities in the lobby and give everyone a taste of science, because science is all around us.
If a visitor comes up and asks you a question, about waves, and you're having a hard time explaining it at one particular exhibit, you can then go to another exhibit and say, here, let me show you on this exhibit what I'm talking about here about this kind of wave.
Tell us a little bit about the partnership with Southern University.
So the Southern University is one of our great partners. They're a historically black university, and they actually also provide docents. The docents are undergraduates mostly, sometimes graduate students, who come here and they'll help us out in the classroom or in the exhibit hall. And the nice thing is that a student who comes here sees them, and they're kind of like the bridge between going from where the student is in the K-12 school system to the university, and then to becoming an eventual scientist. So it helps a lot of people envision themselves as scientists.
So I visited LIGO about a year ago.
Yeah.
And one of my close friends that just graduated in physics, she was a docent here as well. So we were walking around and we were doing some of the activities that they have to offer here as well as the exhibits. So after doing those exhibits, it reminded me of why I got into science. As a child, my father would buy me these science books that'll teach me how to do and let me do different experiments and buy me all the supplies I needed. So as I got older, I kind of, grew away from that.
Yeah.
Because there was other things to do. But coming back here, it re-enlightened my childhood. So it just reminded me why I was a chemistry major.
Part of my job is to work here in the Education Center with the students and share the science that we do, the new astronomy that we're trying to do. It's very exciting, at least for me, it's very exciting. And whenever I'm not working here in the Education Center, I also work as a scientist trying to find the gravitational waves that are buried in the detector noise. So basically, lots of little vibrations from our environment can contaminate the data that we collect and make it difficult for us to find gravitational waves. And we're going to be telling you a lot more about that as we give you a tour of the facility.
So all of your K through 12 and other groups that have physics classes back at their schools and so forth, what do they get here that they don't get in the classroom?
So I think they get that inspiring science. They have essentially When they come here, they have three aspects. They have the tour of this cutting-edge research facility. You go into the control room, and it's like sitting at, the deck of Star Trek or something, right? It's a little bit like our mission control. They also have the exhibit hall. In the exhibit hall, you can interact with these professionally designed exhibits that display science concepts. They have surprising results with that.
What are you doing in here? What's the best thing you've done in this place?
Well, you're going around, you're learning stuff. It's just amazing. I think the very best is the infrared and the normal camera because it tells you like what's infrared and what's not and what can be seen through and what can't be and what reflects from infrared and what doesn't. It's really, really cool.
This giant slinky. This is the most funnest slinky I ever played with.
I really like the infrared thing and seeing how the heat affects the way the lights pick up and the way the different things reflect on like the actual light that we see and then how they don't reflect on the infrared.
And then they have this classroom experience. And the classroom experience is a little more like the classroom experience back at their place, but we use a lot of props and we do a lot of inquiry so that hopefully in this new environment, we're associating the classroom-type experience with the new environment to generate a deeper educational experience.
How the eye works with this PVC tube. When I first got here, we actually used it with toilet paper rolls, but students said something smells weird. So we've actually changed this to PVC tubes. All right, so the wax paper is going to be your what?
Your retina.
Your retina, exactly. And the aluminum foil should be the front of your eye. Is there a pupil yet?
No.
No. So you're going to take the toothpick and poke the tiniest hole in the center, and that will be your pupil. You got that?
Okay.
All right. Do not put the toothpick in your mouth, because I've done that already for you. When we use this, you're going to aim the hole at the object, and if you look at it like this, you won't see anything. You're going to look at the wax paper. And if you look at the wax paper like this, you won't see anything either. So you have to have it about that distance away. Where's the red?
Right.
Good. All right, now pick up your pinhole viewer. On 3 in Vietnamese now. Một, hai, ba. Whoa! Where's the red right now?
The left.
What is happening now?
They're rotating around each other.
Are they rotating?
No, the thing is...
Red on the top. Okay. And now I want you to rotate the tubes again.
Ah, that's cool.
Now, if you think this is cool,
right.
I would recommend going home, making a couple of these for your little brothers or little sisters, and on Christmas, can you imagine what the Christmas lights would look looking through these things? Just don't stand in the middle of the road. All right.
I love seeing the light of understanding and also the light of confusion, because you start off with this look of confusion and then you get people going, aha. And it's those aha experiences you want to maximize, because those aha experiences they don't just mean that they're understanding that concept. It means they're getting excited about that concept. And if you can get people excited about that concept, then you can probably take them and make them into scientists later in life.
So you can actually spread the distance out too.
Yeah. Spread this distance out. But we also do things like this behind me. And those things are often we call them science snacks or science interactives. They are interactives we train teachers often to build for their classes. And they can actually take data from them, and they can use them to not just teach science and educate their students, but to inspire their students, to excite their students. Because we're here at LIGO where we think it's very inspiring science, and we want to take that inspiring science in order to inspire the next generation of scientists. And not just inspire the next generation of scientists, but to inspire you, really, anyone that's out there, to see the science around them.
Well, first of all, just the plethora of ideas that they give us with everyday materials that the kids can actually use and learn and inspire inquiry into their education, and just gives them a little spark to think about something else and what they can do next with what they give them.
Please tell me yes. You can see white? Okay, that's white. Yes.
just to take a simple idea that's so far untouchable before I came here. And now I'm like, oh, really? So that's how that works? You know, it's just the isolation of one thing that explains it so well.
Well, stay tuned for the latest developments here at LIGO, including the new big upgrade that they're doing, and they'll be back online soon with that. And if you want to schedule a school field trip, just do a keyword search on the internet for LIGO Livingston Education Center. And if you just want to come out and visit the place on your own, remember that every third Saturday of the month, they have an open house from 1 to 4. Now, in keeping with our theme of astronomy, our next gym is the Pontchartrain Astronomical Society, and they have an observatory in Washington Parish. Stay tuned.